Hello everyone, this is John Hashmat and welcome to Physics Simply. In this video I will be solving the paper 4 exam for February-March 2020 variant 2. So let's get started. Question 1 says a rocket is launched vertically upwards from the ground. The rocket travels in uniform acceleration from rest. After 8 seconds, the speed of the rocket is 120 meters per second. A says calculate the acceleration of the rocket. We can calculate the acceleration as the change in velocity v minus u over t, final minus initial. So we have the final velocity 120, initial 0, divided by the time 8 seconds. That gives an answer of 15 meters per second squared. Part BI says on figure 1.1, draw the graph for the motion of the rocket in the first 8 seconds. As for time, we have each two divisions represent 1, so this is 6, 7, 8 seconds, and it meets the y-axis at 120. Each two divisions represent 10, so this is 110, this is 120. So we must reach this point from the origin since it was at rest at the start, and constant acceleration is represented as a straight line, like this. Part I says use the graph to determine the height of the rocket at 8 seconds. So using the graph, the distance is equal to the area under the graph, and the area under this graph looks like a triangle. So we have this is the height, which is 120, and the base is 8. So we calculate the area of the triangle equals to half multiplied by the base 8 multiplied by the height 120. That gives an answer of 480 meters. I says from time 8 seconds to time 20 seconds, the rocket rises with increasing speed but decreasing acceleration. That means a decreasing gradient on the graph. From time 20 seconds to time 25 seconds, the rocket has a constant speed less than 200 meters per second. On figure 1.1, draw the graph for this motion. First, we can start with the constant speed, which is a horizontal line below the 200 meters per second speed. For example, starting from this position and horizontal line to 25 seconds, from 20 to 25 seconds. And then we draw a graph of decreasing gradient between the first point here, or the ending point of the straight line, and the start of the horizontal line. So we can draw a curve like this. So this is a decreasing gradient, then horizontal line representing decreasing acceleration, then zero acceleration or constant speed. Question 2 says figure 2.1 shows an athlete crossing the finishing line in a race. As she crosses the finishing line, her speed is 10.0 meters per second. She slows down to a speed of 4 meters per second, and the mass of the athlete is 71 kilograms. Calculate the impulse applied to her as she slows down. So the impulse is equal to the change in momentum, which is mass multiplied by the change in velocity. And we have the mass 71 and the change in velocity, the final 4, and the initial is 10.0. This gives an answer of 426 kilograms meters per second, or we can write it as negative 426 kilograms meters per second. Question BI says define impulse in terms of force and time. We can say that the impulse is equal to force multiplied by time. This is the equation we need to calculate the impulse. I says the athlete takes 1.2 seconds to slow down from a speed of 10.0 meters per second to a speed of 4.0 meters per second. To calculate the average resultant force applied to the athlete as she slows down, we can use the equation force is equal to the impulse divided by time, or change in momentum divided by time. And we already have the change in momentum for 126, and we divide that by 1.2 to get an answer of 355 newtons. Question C says calculate the force required to give a mass of 71 kilograms and acceleration of 6.4 meters per second squared. Here we can use F equals ma, since we have the mass 71 and the acceleration 6.4. This gives an answer of 454.4, which we can approximate to 454 or 450 newtons. Question 3 says figure 3.1 shows a model of a wind turbine used to demonstrate the use of wind energy to generate electricity. The wind is blowing towards the model as shown. Part A says the mass of air passing through the circular area swept out by the turbine blades each second is 7.5 kilograms. The kinetic energy of the air that passes through this circular area each second is 250 joules. Calculate the speed of the air. Since we have the kinetic energy and the mass, we can use kinetic energy is equal to half mv squared So 240 is equal to half times 7.5 times the unknown velocity squared. Placing v as the subject of the formula, it will be equal to the square root of 240 times 2 divided by 7.5. This gives an answer of 8.0 meters per second. Question II says the kinetic energy of the air drives a generator. State the input power of the air passing through the turbine blades. And it says state because the time was 1 second and power is equal to the energy divided by the time. And you already have the energy 240 divided by 1 that gives the same value but with a different unit. The unit for power is watt. Part B says the output current of the generator is 2.0 amperes. The output potential difference of the generator is 11 volts. Calculate the output power of the generator. We can use the electrical power equation. Power is equal to voltage multiplied by time, or potential difference times time. We have 11 multiplied by 2. That gives an answer of 22 watts. Then I says calculate the efficiency of the wind turbine. We calculate that as the output power divided by the input power multiplied by 100 to get a percentage. And the output is the electrical power, which is 22. The input was the kinetic energy due to the wind, which was 240. And we multiply that by 100 to get an answer of 9.16 recurring. So we can approximate that to 9.2%. Question C says the density of air is 1.3 kilograms per meter cubed. Calculate the volume of air passing through the circular area swept out by the turbine blades each second. And each second we had a mass of 7.5 kilograms of air passing. So we have the mass and we have the density. So the volume is equal to the mass divided by the density. So 7.5 divided by 1.3, that gives an answer of 5.769 and some more digits. We can approximate that to 5.8 meters cubed. Question 4 includes latent heat capacity, which was removed from the syllabus, so you can skip this question. Part A says define the specific latent heat of fusion of a substance. It is the energy needed to change the state of a unit mass from liquid to gas at constant temperature, since the temperature does not change during the change of state. Part B says small pieces of ice at 0 degrees Celsius are added to 0.35 kilograms of water. The initial temperature of the water is 24.5 degrees Celsius. The temperature of the water decreases to 0 degrees Celsius. The water loses 35,000 joules of thermal energy. As it cools, all of the ice added to the water also melts. The specific latent heat of fusion of ice is 3.3 times 10 to the power of 5 joules per kilogram. I says calculate the specific heat capacity of water. We have the mass and the initial and final temperatures, and we have the energy gained. So we use energy is equal to the mass multiplied by the specific heat capacity and the change in temperature. Q is equal to 35,000, M is 0.35, C is the unknown, and the change in temperature is the difference between 24.5 and 0. So C is equal to 35,000 divided by 0.35 multiplied by 24.5. This gives an answer of 4,081.63, which we can approximate to 4,080 joules per kilogram degree Celsius or Kelvin. I requires the mass of ice added to the water. We can use the same energy. Q is equal to ml in this situation because it's a change in state. And Q is still 35,000 and the mass is the unknown. And the latent heat of fusion is 3.3 times 10 to the power of 5 from the question. So we divide the energy by 3.3 times 10 to the power of 5. That gives an answer of 0.106 or 0.11 kilograms. Question 5a says complete the sentences with words that describe the main process of thermal energy transfer in each case. A man goes for a walk on a cool day. He touches a metal gate which removes thermal energy from his hands by conduction, since there is contact between two objects. So this is conduction. He holds the sides of a cup containing a hot drink. His hands gain thermal energy by, again, conduction, since there is still contact between two objects. Some farm workers have lit a fire. The man warms his hands by the side of the fire. His hands gain thermal energy by radiation or infrared radiation, since by the side means that the heat is not going upward, so it's not convection. And the air between the man's hands and the fire is actually a poor conductor, so it's not conduction that transmits the heat. Question B says, describe in terms of particles the transfer of thermal energy through the metal of the gate after transfer from the man's hands. We can say molecules vibrate faster and transfer energy by collisions, and free electrons also move through the metal from atom to atom. Question C says, figure 5.1 shows a car on a sunny day in a hot country. The object labeled A is placed inside the windscreen. It is used by the owner of the car to reduce the temperature rise of the air in the car. Ring the most suitable material for the outer surface of object A and explain your choice. So we have colors here, dull black, dull white, shiny black, or shiny white. So we use shiny white because it reflects sun rays or reflects infrared radiation. So we can say that a shiny white is a good reflector, or we can say that it is a poor absorber of infrared radiation or heat radiation. Question 6a says, figure 6.1 shows crests of a water wave moving from left to right on a harbor. On figure 6.1, draw 3 more crests to the right of point A. So we have a corner here. This means there will be diffraction. So first, if we use a ruler to continue the line of the direction of the wave and measure the distance between the wavefronts, so the wave keeps moving forward and the wavelength does not change. The wavelength here is approximately 1.6 centimeters. So measuring from the start of the last wavefront, we have 1.6 here, and then we add 1.6 again, so it will reach 3.2. Extending the line, we add another 1.6 here. So these are the positions for the extra wavefronts. Now we draw the wavefronts. Since this is a large gap, we will draw straight lines that are perpendicular to the direction of the wave. Add the points we've marked, equally spaced, like this. And then we are going to add small curves that get larger with distance to represent the spreading of the wave. Double I says, state the name of the wave process that occurs as the wave passes point A. It is called diffraction of waves. Part B says, figure 6.2 shows the crests of another wave moving from left to right in a different part of the harbor. This wave moves from deep water into shallow water. On figure 6.2, draw an arrow to show the direction of movement of the wave after it has passed into the shallow water. The direction is always perpendicular to the wavefronts, so this is the direction, 90 degrees on the wavefronts. So this angle is 90. Part double I says, state the name of the process that occurs as the waves pass into the shallow water. So from medium to medium and changing speed, that is called refraction of waves. Triple I says, complete table 6.1 to state whether each of the properties of the wave increases, decreases, or stays the same as the wave passes into the shallow water. Moving into the shallow water, the wave bent towards the normal and the wavelength actually decreases. So the first one is easy because the wavefronts became closer, so it decreases. The frequency through refraction stays the same, it does not change. And the speed follows the rule of the wavelength, since speed is equal to frequency multiplied by wavelength, and frequency is the same. Since wavelength decreased, then speed also decreases, same as wavelength. Question 7a says, figure 7.1 shows a converging lens and the image I formed when an object is placed to the left of the lens. The principal focuses are labeled A and B, and the center of the lens is labeled C. On figure 7.1, draw 2 rays to locate the position of the object, and draw the object and label it O. So first we have an easy ray that passes through the optical center without bending and reaches the image. So we can just draw from the tip of the image a straight line through the optical center and extend it to the left. Another ray passes through the focal point, so from the image through the focal point, like this. And then we draw an exactly horizontal line, which means perpendicular on the central line of the lens, from this point to the left. So we must make sure that this angle is actually 90 degrees, so we can use a protractor to do that. And these are the directions of the rays going to the image, and they originated from this point. Since the tail of the arrow of the image is on the principal axis, then the tail of the object is also on the principal axis, and the rays came from the head of the object. So we draw the object as a vertical arrow with its head at the top like this. And it said to label the object O, so we labeled this O. Part double I says, ring all of the following distances that are equal to the focal length of the lens. So this is the focal length and this is the focal length. So AC and CB. Part B says figure 7.2 shows green light passing through a triangular glass block. Red light enters now the triangular glass block shown in figure 7.2 along the same path as the green light. Part I says on figure 7.2 draw the path of the red light within the triangular glass block. So red actually bends less than green. So this was the original direction of the ray. It bends toward the normal, but not as much as the green light. So we are going to draw it like this. We do not have to measure a specific angle, and then we draw the arrow direction. Now the question says figure 7.3 shows green light passing through a rectangular glass block. Red light enters the rectangular glass block shown in figure 7.3 along the same path as the green light. On figure 7.3, first draw the path of the red light within the rectangular glass block and then draw the path of the red light after leaving the rectangular glass block. We are going to do the same thing, entering the glass. Again, we are not going to continue in the same direction. We are going to bend towards the normal, but not as much as green. But since we have parallel sides entering and leaving, the exiting ray will be parallel to the green ray. So we have the arrow here with different angle, but the direction of the red ray will be parallel to the direction of the green ray and parallel to the direction of the original ray. Question 8 says figure 8.1 shows a circuit. We have a 12-volt supply in series with a 3 ohm lamp, a 2 ohm resistor, and a 6 ohm wire XY, and an ammeter. And the length of the wire is 2.0 meters. The lamp has a resistance of 3.0 ohms. Line XY represents a uniform resistance wire of resistance 6.0 ohms. Part A says calculate the reading on the ammeter. I is equal to V over R, and the total voltage was 12 volts. The total resistance of all these in series is 6 plus 3 plus 2. So we get an answer of 1.0909 recurring. So we can approximate that to 1.1 amperes. Part B says figure 8.2 shows the circuit with a different connection to the resistance wire and an added resistor. The length XY of the whole resistance wire is 2.0 meters. The contact is made at Q where the distance XQ is 0.60 meters. Calculate the resistance of the circuit, the whole circuit now. So this section here is actually two resistors in parallel. So we have 1.5 ohm resistor in parallel with another resistor which has a resistance equivalent to this length of the wire. So we need to know the resistance of this part of the wire. The length is directly proportional to the resistance, so we can use cross multiplication. We can say that if 2 meters have a resistance of 6.0 ohms, what does a length of 0.60 meters have? So multiplying 0.60 by 6 and then dividing by 2, that gives us an answer of 1.8 ohms. So the 1.5 ohm resistor is in parallel with 1.8 ohms. And then we have a 2 ohm resistor in series and a 3 ohm lamp in series. First we calculate the part in parallel and then we add the resistors in series. Applying this, we can use product over sum for the parallel part. 1.5 times 1.8 divided by 1.5 plus 1.8. And we add then the resistance in series 2 and 3. This gives a total resistance of 5.81818 recurring, so we can approximate that to 5.82 ohms. Question 9 is about logic gates, so you can skip this question for the new syllabus. Part A says state the name of the logic gate with the symbol shown in figure 9.1. This would be a NAND gate. Part B says state the name of the logic gate with the truth table shown in table 9.1. So 0 changes into 1 and 1 changes into 0. So we are basically reversing the input. So it's a NOT gate. Part C says figure 9.2 shows a digital circuit. We have two inputs A and B going to an OR gate and also the same inputs going to an AND gate. The output of the OR gate is C, the output of the AND gate is D, and these outputs are inputs to a NAND gate with an output E. Complete the truth table in table 9.2 for this circuit for all possible combinations of input. First we go through the output E from the NAND gate. It is the opposite of an AND gate, and AND gate gives only 1 as an output if both inputs are 1. the NAND gate would give output 0. So for 1 and 1, there should be 0, and the rest will be 1. As for the OR gate, it only gives out an output 0 when both inputs are 0. For C, 0, A, B should be 0 and 0. And for the AND gate, it only gives an output 1 if both inputs are 1. So A and B should be 1 for an output 1, and the rest would be 0, 1 or 1, 0. Question 10a says figure 10.1 is a simplified top view of a flat coil. There is an alternating current in the coil. Describe the magnetic effect of this alternating current. We say that the current in the coil creates a magnetic field around it that keeps changing magnitude and direction also, because the alternating current keeps changing magnitude and direction. Part B says figure 10.2 shows a pan placed above the coil. The base of the pan is made of steel, which is a conductor. State what quantity is induced in the base of the pan. We can say electromotive force or EMF, or we can say voltage. Part C says the pan contains water. State and explain the effect of the quantity induced in Part B on the temperature of the water in the pan. We say that the EMF induces a current in the pan, which heats the pan, and then heat is transferred to the water, causing its temperature to rise or increase. Question 11a says the isotope hydrogen 1 has a proton number 1 and a nucleon number 1, so it's made up of 1 proton and no neutrons. Two isotopes of helium are helium-3 and helium-4. Helium-3 has a proton number 2 and a nucleon number 3. Helium-4 has a nucleon number 4 and the same proton number since it is an isotope. Complete table 11.1 for neutral atoms of these isotopes of helium. So for a neutral atom, we have the same number of protons and electrons, and the proton number was 2, so the number of electrons in both atoms will be 2. As for the number of neutrons, it is the difference between the nucleon number and the proton number. So for helium-3, it is the difference between 3 and 2, and for helium-4, it is the difference between 4 and 2. So for helium-3, 3 minus 2 is 1, and 4 minus 2 is 2. Lastly, we compare the mass to a neutral atom of hydrogen 1. So for helium-3, the comparison is from 3 to 1, so that is 3 times, and 4 to 1 for helium-4, so it is 4. So 3 for helium-3 and 4 for helium-4. Part B says an experiment takes place in a laboratory shielded from all background radiation. A sample of radioactive material is wrapped in aluminium foil. A sample of radioactive material is wrapped in aluminium foil of thickness 0.1 millimeters. A detector of ionizing radiation placed 1 centimeter from the foil records a reading. A piece of aluminium of thickness 5 millimeters is placed between the detector and the foil. The detector reading drops to 0. State and explain any type of radiation passing through the aluminium foil. We say that would be beta particles or beta radiation, since it can penetrate the foil but can't penetrate 5 millimeters of aluminium. And there is no gamma since the reading dropped to 0. And there is also no background, so 0 means nothing passing through the 5 millimeters of aluminium. So this was the end of the exam. I hope you enjoyed this video and found it useful. Keep practicing, and I will see you in another video.